So in this video, I am going to present to you the proof of the intermediate value theorem. There are three essential things that we need to go over. The first thing is the definition of connected sets. Then we need to prove a lemma that continuous functions map connected sets to connected sets. And then finally, we will write the proof of the intermediate value theorem. So firstly, let's begin with the definition of connected sets. It's a pretty straightforward definition. It states that a set S is disconnected if and only if there exist two non-empty subsets S1 and S2 such that S1 union with S2 is equal to S, S1 intersection with the closure of S2 is equal to the closure of S1 intersection with S2, which is equal to the empty set. And then S is connected if it is not disconnected. So in order to better understand this definition, let me just quickly give you a few examples of sets that are connected and then disconnected. So the best way to do that is to visualize. So I'm just gonna create this XY plane and then create a set in here. Let's say that this is the set S. So the shaded region is the set S. Now you can clearly see that this set is disconnected, and the way you do that is you label this first part S1 and you label this second part S2. Then clearly S1 union with S2 is equal to S. We also know that the intersection of S1 with the closure of S2 is the empty set, and then the intersection of S2 with the closure of S1 is also equal to the empty set. And those are the three conditions that we need for a set to be disconnected. Another example of a set, for example, that is connected would be this one. So this one is a little bit of a difficult example to prove, but there you go. So this set is connected because you can never find a disconnection for it. So given any sets S1 and S2, two non-empty subsets S1 and S2, their union will, one of these conditions will actually not be satisfied. Either their union will not be S, or the intersection of the first set with the closure of the other set will never be the empty set. Now, you might wonder, how do we go about proving that? And the idea is that it's actually hard to prove this directly, which is why we sometimes use an associated concept, which is called arcwise connected or pathwise connected. Either one of them, they mean the same thing. And what this essentially says is that a set is arcwise connected or pathwise connected if and only if for any 2 points in that set, there is always a path that lies in the set that joins those 2 points. So what I essentially mean by that is, if I have this point and let's say I have this point right here, then this set is path connected if for any 2 arbitrary points, I can always draw a line that joins those 2 points, and that line needs to lie inside the set S. Let's label this S prime, and that is S. Now consider this set S for a second. You can clearly see that the set S is actually not path connected, because if I draw a point over here and if I draw a point over here, both of these points are in S, but if I want to join it, let's say I use this line, I use this line, does not matter what line I use, there will always be a portion of that line that will not lie in set S. So one thing that I would like to emphasize over here, that it is true as a theorem that if a set is R, if a subset of R to the power of n is arcwise connected, then it is also connected. But the converse of that statement is not true. A set which is connected need not be arcwise connected. I leave that to you. So see if you can come up with an example of a set that is connected but which is not arcwise connected. Yeah, so let's move on to dilemma now. So before we move on to dilemma, actually there is an exercise that I'm going to leave for you guys. Sorry about that. And the exercise is as follows. This is a sort of a lemma, I would say, because I'm going to use this in the proof of the intermediate value theorem, but I'm just going to assume that it is true. The proof of this is quite straightforward. So the exercise is that if S, which is a subset of R, is connected, then S must be an interval. So the idea is that if you restrict yourself to the real number line, then the only sets that are connected are the ones that can be written as an interval. So consider the set 2 comma infinity, does not matter 2 comma 3, you have negative infinity comma 2, does not matter what kind of set it is, as long as it is an interval, it is connected. Now on the other hand, if it is not an interval, then it is not connected, which is precisely the contrapositive of the statement that you should try to prove on your own. So, and actually, the best way to write out the proof for this is to use the contrapositive to assume that S is not an interval and then show that S is not connected. That is probably the best way to go about writing this proof. But for the purposes of this video, I'm just going to assume that this theorem is true, and I'll use it when I'm proving the intermediate value theorem, and maybe also when I'm proving the lemma. So, now let's move to the lemma. So this is I would say that the proof of the intermediate value theorem is actually quite short and it's quite simple, and it's actually the lemma that is relatively harder to prove. It's not, objectively speaking, it's not a very hard proof, but it is definitely, in my opinion, it is a little bit trickier than the proof of the intermediate value theorem itself. Although maybe one could argue that you can't prove the intermediate value theorem without this lemma, so maybe this lemma is just a part of this proof. Anyhow, so the lemma states that continuous functions map connected sets to connected sets. In other words, if S is a connected set and f is a function that maps from S to r to the power of m, then f of S is also connected. So let's write out the proof of that lemma. So let's begin with the proof. So I'm going to assume that, I'm going to say let S be a connected set, a connected set. And I'm also going to say that f be a function that maps from S to r to the power of m, be a continuous function, be a continuous function. Okay, so normally, actually, you know what? I'll just write this out as let S be a set. Let S be a subset of r to the power of n. Let's not assume anything for now. So normally what I need to do is, in order to prove this lemma, I need to assume that S is connected, and then show you that f of S is also connected. What I'm going to do instead is I'm going to use the contrapositive. I'm going to assume that f of S is disconnected, and then I'm going to show that S must also be disconnected. So I'll use the contrapositive. So what my assumption will be is I'm going to assume f of S is disconnected, and I want to show S is also disconnected. S is also disconnected. Okay, so consider this as or not as, let u1 comma u2 be a disconnection of f of S, and of course that means that u1 union with u2, okay, maybe not the best of choices, let me change this to something else. Let's say it's v1 and v2. So v1 union with v2 is equal to f of S, and then v1 intersection with the closure of v2 is equal to the closure of v1 intersection with v2, which is equal to the empty set. So this we know is true because of our assumption that f of S is disconnected. Okay, so now what I want to show is that there exists a disconnection of S. So now what I'm going to do is I'm going to say let S1 be equal to the set of vectors x in r to the power of n, or x, maybe I should just say in S, x in S. such that f of x is in U1 and S2 be equal to the set of vectors x and s, or points in S, such that f of x is in U2. Now, one thing that you should immediately see over here clearly, I'm going to write out over here clearly, as U1, or once again, this should be V1 and V2, as V1 and V2 are both non-empty, S1 and S2 are also non-empty. So this is clearly follows from this piece right here. I mean, if there is at least one element in V1, then there must be at least one element in S1 and so on. Okay, so then S1 and S2 are non-empty, and also as V1 union with V2 is equal to f of s, it follows that S1 union with S2 is also equal to S. And why is this true? I mean, think about this. Let's say that I have let's say that this is the pre-image and then this is the image of set S under F. So this is f of S, and let's say that this is set S. For now, I'm going to assume that that is disconnected. So let's say this is S and this is so this is S1 and this is S2, and let's say that these are sets V1 and V2. Now, what I'm saying is, since V1 union with V2 is all of f of S, the pre-image of V1, which is S1, and the pre-image of V2, if I union them together, that will give me the domain of F. Because what I've assumed over here, or the way I've set up this question, is I've assumed that f of S is the image of F over all of its domain and not any arbitrary subset of its domain. You could do this by assuming that S is a subset of the domain of F, but for the time being, I've assumed that it's all of its domain. So the pre-image of all of its domain is S1 union with S2 because of the very fact that V1 union with V2 is its range. So this is why S1 union with S2 must equal S. However, the one thing that I need to show now is that S1 intersection with the closure of S2 is equal to the empty set. And what I'm going to do is I'm just going to prove the fact that S1 intersection with the closure of S2 is not equal to the empty set. Proving that S2 intersection with the closure of S1 is not equal to the empty set is extremely similar. It's nothing new. It's the same idea all over again. So what I'm going to do now is I'm going to show instead that S1 intersection with the closure of S2 is equal to the empty set. So I'm going to show, I'll now show that S1 intersection with the closure of S2 is equal to the empty set. So assume by contradiction that there exists that there exists an element X, or let's label something else. Let's say A in S1 intersection with the closure of S2. Then what we get is A must be an element of S1 and A must be an element of the closure of S2. So this is where you have to be a little bit careful. What I'm basically just going to do is I'm going to show you that, or basically what I'm going to show is that if A is in S1, then A is also in f of A is in V1. That is true, but you have to be very careful when you're dealing with what happens if A is in the closure of S2, because you can't just say that if it, I mean, you can't assume that if A is in the closure of S2, that it must also be the case that A is in the closure of V2, because of the fact that the closure of S2 need not be in the domain of F. So, because I mean, consider this: what happens if F is defined over two open intervals? This is S1 and S2, then F is not even defined on the closure of S2. So you can't just say that, well, if A is in the closure of S2, then F of A is in the closure of V1, because F of A is not even defined if A is in the closure of S2. I mean, it does get a little bit complicated because we already assumed that A is in the closure of S1. Sorry, A is in S1, so it must be in the domain. But we need to, get rid of this complication. And there's a very simple way to do that. So I'm gonna come to that in a minute. So A is in S1, and we know that A is also in S2, and A is in A is in the closure of S2. Then so the first thing I'm going to do is say then, where A is in S1 implies that f of A is in V1. So that's the first thing. So we know that if A is in S1, then it must be the case that f of A is in the closure of, f of A is in V1. That just follows immediately from the fact that A is in S1. There is no complication over there. F of A is well defined. Now, we need to deal with this part right here. We need to see what happens if A is in S2. So what I'm going to do instead is I'm going to say, well, if A is in the closure of S2, then there must exist a sequence in S2 that converges to A. So what I'm going to say now, so we know that this is true. In fact, let me just put this over here. Also, as A is in S2, the closure of S2, there must exist a sequence, let's say A of n, which is completely contained in S2, such that A of n converges to A. Then, as f is continuous, it follows that limit as n approaches infinity of f of A of n is equal to f of limit as n approaches infinity of A of n, and this is equal to f of A. Thus, by definition, f of A is in the closure of V2. Why? Because there exists a sequence in V2, which is f of A of n, that converges to f of A. So directly from the theorem that I proved, I guess, in a couple of videos ago, it follows. It basically, the theorem says that a point lies in the closure of a set if and only if there exists a sequence in that set that converges to that point. So we've shown that f of A is in the closure of V2. We've also shown that f of A is in V1, but here's the contradiction. Thus, or hence, or moreover, this implies, or let's label this 1 and let's label this 2. By 1 and 2, f of A is in V1 and f of a is in the closure of V2, and this implies that f of a is in V1 intersection with the closure of V2. And this is a contradiction because by our assumption, this was equal to the empty set. Remember, we initially assumed that V1 intersection with V2 is the empty set because V1 and V2 forms a disconnection of F. Hence, we have a contradiction. We have a contradiction. Thus, S1 intersection with the closure of S2 is equal to the empty set. And then I can say likewise, the case is very similar. If you want to prove this if you want to be completely rigorous and you want to go ahead and prove that the closure of S1 intersection with S2 is the empty set, you can do that. The only thing that will change, like literally, you can just copy paste this entire thing and change S1 to S2s. Wherever you see an S1, just replace that with an S2. Wherever you see an S2, replace it with an S1. Same thing. Wherever you see an V1, replace that with a V2, and then wherever you see a V2, replace that with a V1. But I would like to encourage you to write that case on your own. See if you actually understand what's happening. Likewise, the closure of S1 intersection with S2 is also equal to the empty set. Therefore, S1 comma S2 is a disconnection of S, and hence we've shown that S is disconnected. So that's the first part of the proof. This is the lemma that we've just shown. So we have proven that continuous functions map connected sets to connected sets. And if you understand what's happening, we're basically done. So here's this, before I write out the proof of the intermediate value theorem, here's the idea. So we've assumed that f is, in the intermediate value theorem, the statement is that suppose f is a function that maps from S. So S is any arbitrary subset of R to the power of n, and it maps from that set to R, and it is a function that is continuous everywhere in S, and V is a subset of S which is connected. So V is the connected set. And then we assume that if vectors A and vector B are elements of V, and f of A is less than t, which is less than f of B, then there is a point C in V such that f of C is equal to C. So in other words, given any 2 points, let's say this is f of A and f of B, and as long as the function is continuous, then you have a point that lies between f of A and f of B, then there exists a point at, if you evaluate the function at that point, you will get the value between f of A and f of B. So let's say that this is f of A, and this is f of b. Let's say this is a point C, then or I'm going to label this C, then there exists a C such that f of C is equal to B. That's basically the idea. Now, what is the plan? How are we going to go about proving this? While the proof is extremely short, here's the idea. We assume that V is connected, so therefore f of V is also connected. That is basically, that follows from the fact that continuous functions map connected sets to connected sets. So we know now that f of V is connected. What we know even more, what we know further, is that f of V must be an interval. That follows from this exercise, because remember, f of V is a subset of R. F is a function that maps from S to R, therefore it must, and V is a subset of S, so it must be the case that f of V is a subset of R, and thus f of V is basically an interval. And f of A and f of B are any arbitrary points that lie in that interval, and therefore we know that every point that is in between f of A and f of B must also be in the interval, and that's basically the proof. So let's go ahead and write that out. So now this is the proof of the intermediate value theorem. Here's how we're going to start. Let f be a function that maps from S to the set of real numbers, be a continuous function, Also, let V, which is a subset of S, a proper subset of S, be a connected set, uh, okay, be a connected set. Then by the exercise and the lemma, so I'm gonna, okay, by the exercise and the lemma above and the lemma above, f of v is a connected set, is a connected set in R, in R. Thus, f of v must be an interval. Must be an interval. Moreover, f of a comma f of b are elements of f of v. So both f of a and f of b lie in that interval f of v. Thus, everything, or thus as I should still say that as f of v is an interval, is an interval, what I'm basically going to say that every point between f of a and f of b also lies in f of v. So as f of v is an interval for all t in the set of real numbers, if f of a is less than or equal to t, which is less than or equal to f of b, then t is an element of f of v, which implies, of course, that there exists a c in v, there exists a c in v such that f of c is equal to t, and that completes the proof. So one thing that you might feel, I mean, uh, a little bit of a cheat is this idea that f of v is an interval, and therefore, since f of a and f of b lie in that interval, everything in between is also in that interval. I mean, it's just, I mean, at first when I saw this proof and when I first did this proof, I also thought that, but I mean, I guess it's trivial enough to be, it's trivial enough to be used without a proof. Because if you think about it, you can actually go ahead and write out this proof of, even more rigorously by dealing with each type of interval in R separately. I mean, you would have to deal with closed sets, you would have to deal with open sets, semi, well, I don't know what semi-open or semi-closed, whichever you want to call them. And then you would also have to deal with sets. So let's just say this is A and B, where A and B are real numbers, all of them, A and B, A and B, A and B, and then you would also have to go ahead and use this A infinity, closed A and infinity. You would do negative infinity comma A, and then negative infinity comma b. So you would have to go through all of these intervals, because these are all the different kind of intervals, unless I missed something. But you would have to go through all of these um, different intervals, and then show that if f of a and f of b are elements of any one of these type of sets, then everything in between will also be in there. But I mean, once you understand what the very concept of interval is, it's you can just overlook that completely. Because if you think about it, what are, I mean, if you have a set in S that is not an interval, then it must be, what does that set look like? So I mean, if it, or how do you write out that set? So if it's not an interval, then it must be a union of intervals, a union of disjoint intervals. So if you think about it, negative 2 comma 3 union with, let's say, 4 comma infinity. Now this is a disconnected set. It's not an interval, but it's always a union of intervals. You can always have it might sometimes even be an infinite union, but it is a union of sets. That's the key thing over here. If you graph this out, it's basically the number line from negative 2 to 3, and then it's everything from 4 to infinity. So yes, something like this, from negative 2 to 3, and then everything greater than 4. So nothing between 3 and 4 is in the set. But that's basically the idea behind this, because as long as you can write a set in R as an interval, and as long as you have 2 points that lie inside that interval, it is trivially true that every point between those 2 points will also lie in that interval. Once again, as I said, you if you want to prove that completely rigorously, you can prove that for each one of these cases. It's not a very hard proof. It's quite simple. In fact, if you know what convex sets are, and if you have dealt with convex sets, then you probably already know how to write out that proof. But I'm not going to go into that detail because, well, you have to deal with the 8 different cases. So yeah, that is. By the way, if you study this proof in your analysis course, I also believe that they will probably just leave it to this point and not go into that much detail, or they would not actually go into all those cases because it's unnecessary. This is sufficient. So yeah, that is the proof of the intermediate value theorem. It is a relatively shorter proof. It's not as long as, let's say, the proof of the extreme value theorem. But yeah, that is it for this video. In the upcoming videos, I plan on proving a result about uniform continuity, and then I'm planning on also proving the chain rule and then the mean value theorem for multivariable functions. So yep, well, that's pretty much it for this video. I hope you enjoyed it. I'll see you in the next video.